Today we're going to go over the heaps. Actually, you are supposed to learn in data structure class, but last year we had some situation. So just in case you didn't learn the heap sort in data structure class. First, we have to understand the binary tree. Binary tree has complete tree. Complete tree means whenever you have a new node, the node will be added to the left, all the way left of the lowest level. So there's a level 0, level 1, level 2, level 3. So when I have 9 data, I should build all the way up to level 2 first. Then on the level 3, all the items should be the children of the leftmost node. That is the complete tree. Then complete binary tree. If we have a complete binary tree, we can guarantee there is no gap between data in the list. Then also we can calculate the child very easily. To calculate the child very easily, we did dummy 0. That means we are not using index 0 at all. Too easy for calculation. But even though you use index 0, you can still calculate the children, but the calculation becomes harder, more complicated. If you start from 1 to child, 2 child, left will be 1 times 2. Then right child will be 1 times 2 plus 1. So we can use 2 times k and 2 times k plus 1. So 2 times parent number plus 0, 2 times parent number plus 1. Now from 2 to the 4 and 5 is the same thing. 2 times parent number, parent index plus nothing. 2 times parent index plus 1 is 5. How about the index 3 children? 6 and 7 is also 2 times 3 parent number, then 2 times 3 plus 1 parent number times 2 plus 1. So you can see there's a certain rule we can apply. So 2 times 4, 2 times 4 plus 1 here. So data is in by level 1, 2, 3, 4, 5, 6, 7, 8, 9, and actually the data is inside of the list. So those numbers of 1, 2, 3, 4, 5, 6, 7, 8, 9 means index number of the list. So there is a list. Also the heap, max heap means we are going to use max heap. Minim means each node is smaller than its children. That means max heap is each node is greater than its children. So we can check if it's max heap or not. 99 is greater than 80 and greater than 85. 80 is greater than those two children. 17 is greater than 2 children. 85 is greater than 2 children. So every parent is greater than its own children. So this is max heap. Max heap guarantees the maximum value is at root. So this is very important to know. In the min heap guarantees minimum value is at root. In this case 1. Then root parent is always less than children. Now this min heap, max heap is also listed in here. Actually this is the real data structure. And this tree is our imaginary data structure. That means actually we do not build a tree. We just use list only, but we think like it's a binary complete tree. So real data is a list. Let's see exercise number 1. Which of the following trees is a heap? 88 is greater than children. 66 is greater than children, but 44 is not greater than children. So this is not. Then 55 if you see here, I don't see any evidence of this one looks like in order 22, 33, 44, 55, 66, 77, 88. See, 66 and 77, 88 is greater than them, and 66 is okay, parents. 77 is also okay, parents, so this is also max heap. Then D looks like max heap, but it's not complete, so this is not max heap. Heap must be a complete binary tree. This one is a complete binary tree. Then if you see here, yes, this is also max heap. The last one is not binary tree, so this is not heap. In number 2, which of the following arrays have the heap property? That means you are actually supposed to draw the heap. So if I draw A first, 99, 88, 66, 44, 33, 55, 77. This one does not make it. So it's not. Then B, 99, 88, 77, 66, 55, 44, 33, then 22. Yes, this one is a heap. Then C, 99, 88, 44, 77, 22. Yeah, so far good. 33, 55. No, because of this. No. Then, yes, this time I'm going to use just a list. 99 compare with 2 times 1 and 2 times 1 plus 1. Then, it's okay. Then 88 children is 2 times 2, then 2 times 2 plus 1. 77 and 22 are smaller than 88, so it's good. Now, 3 the children is, so 3 the children is 3 times 2, then 3 times 2 plus 1. 33, 44 are smaller than 66. Now, finally, I'm done. 1, 2, 3. Then starts from 4. 77 for the child is 8 and 9, but there's an up to 8. Then 55 is smaller than 77, so this is true. We can think about how to add an item to the heap. You are going to make it heap down. So let's say insert a value. Let's do heap down. For variety, we will use char data. Let's just put in the new value at the root. For example, put in B, heap down, swaps. So let's just say I'm going to insert B here on the root. Then compare with 2 children. But I don't have to compare with each children. I need to compare 2 children to each other first. If there is a children, compare 2 children each other. Oh, E is bigger. So now compare with E and current B. So now root becomes E, current becomes B. Number 2, child becomes E, B. Then starts from what I swapped. So now I start from number 2. Then check if it has 2 children. Yeah, there's 2 children. Now compare between children, C and D. Oh, D is bigger, so D is chosen as a bigger child. Then compare with root, parent. Then B and D. Oh, D is bigger. That means swap. Now I'm gonna start from the current, what I swapped. Then check if it has 2 children. Oh, there's only 1 child. That means compare with this one child. If parent is smaller, swap. This case parent is not smaller, so you don't have to swap. So finally, you're gonna have EDD, CBAC, ABB. EDD, CBAC, ABB. This is a hit down. So you can think about how to write the code of hit down. Size will be the last index. It's gonna be size because if I use the size as a last index, I can just pass it to the swap method. You can think about. You're going to calculate children. That means you're going to check 2k and 2k plus 1 as 2 children. Now, if the children are out of range, you count. That means if 2k is bigger than size, you don't have to check it. This means 2k is bigger than size. Compare the children and take the largest. In this case, actually, you can see if there's only left child or only left and right children. So you can check left child exists. If right child is not exist, you are going to assign largest as left. If right child exists, you are going to compare left and right child. Then by comparing left child and right child, assign the largest to the like a maximum child. So there, if right is bigger, assign largest as right. Then by using the largest child, compare with the parents, then swap. So before that, do a swap if parent is smaller than child. So largest child, in that case, swap. If you swap, you have to keep doing from the current position. In this case, weaker from the largest, that means the child position. You swapped. You're gonna restart this hit down. So those two things will happen only if current, the parent, is less than largest child.